Thank you. Okay, so today we will talk about the electrical circuit and qubit interaction in silicon and superconducting qubit. Imran will be in charge of the silicon qubit, and I will talk about the superconducting qubit. This is the agenda. We will do some self-introduction and maybe advertisement, but very quick, not going to waste you too much of time. I will go with the first part just to review some of the basics of quantum computing, so you can get so that every one of us are on the same page. And then Imran will take over, talk about how to use silicon qubit to achieve what hardware we need in the silicon qubit to achieve the basics of the quantum computing, right? And then in the afternoon, I will talk about how the superconducting qubit architecture is used to achieve the corresponding purposes. I will also give a demo on superconducting qubit chip design. Okay, so the first hour will be part one, and I need to make sure I don't run over the time, right? So I will first review the basics, but before that, just advertisement. I have a book on introduction to quantum computing. I have it here with me. I can pass around later. I also have some YouTube channel on introduction to quantum computing and hardware. You can watch for free. I also have another book coming up by the end of this year. It's about quantum computing hardware architecture. So I'm an electrical engineer. I try to write down my experience of learning quantum computer from an electrical engineer's perspective. We can discuss more if you are interested. I came from San Jose State U. It's a university in the Silicon Valley. It is a minority survey institute with a lot of students. In our master degree, we have a concentration on quantum information and computing. And you see that we only have 3 classes. One is the algorithm, one is related to low temperature electronics, another is related to quantum computing architecture. You will see that this almost involve no quantum mechanics. So I think electrical engineer have a very important role in the quantum computing industry. We also have a Quantum Technology Master of Science funded by the NSF, and it is a collaboration between the physics and electrical engineering. If you're interested, we can discuss more later. So let's go ahead on the basics of quantum computing. Can I have a quick survey? Who already knows some of the basics of quantum computing? Right. Who don't know anything about quantum computing at this moment, or not much? Thank you. Yeah, so I will talk about the basics, but I will also be quick to make sure that we cover the essential, right? So what is quantum computing? The most important thing, it uses the superposition and entanglement. These 2 important quantum mechanics principle. And one more important thing is interference, because without interference, you won't be able to design an algorithm to get the data that you want. There are 2 types. One is gate-based, another is annealing, right? And there are lots of applications, right? For drug design, it is promising. If we have error-corrected quantum computer, then we can speed up a lot of scientific computation exponentially, including the optimization problems. Quickly, what is superposition, right? In classical computer, we use 0 and 1 to represent the state, right? You can use head or tail, happy or sad, and here we use transistor on and off. In quantum computer, you have so-called basis state. If you force it to only use the basis state for computation, it is just the same as a classical computer, right? Here I put the so-called Dirac notation, but we don't need to worry about this. But basically, again, you have 0 and 1, or even transistor on and off. If you only allow it to compute on the basis state, they are exactly the same. And of course, the most important thing about quantum computing is that we allow superposition, right? So what does it mean? It is like a spinning coin on the table. You don't know whether it's up and down. This is just an analogy, not an accurate one, right? And it can be a superposition, a linear combination of head and tail, right? So that means we have more profound information in quantum mechanics. Why this is a big deal? In classical computer, if I have 4 bits, I can have 16 possible values from 000 to 1111. Again, if in quantum computer, I limit them to only the basis states, I only also have 16 possible basis states. Remember earlier, if I only have 1 qubit, I can have 0 and 1 basis state. Now I have 4 qubit, I can have 0, 0, 0, 0 all the way to 1, 1, 1, 1. I have 16. But we allow to have a state which is in the superposition of this. That means for a state, it can be described, it needs to be described by 2 to the power 4 compressed numbers. So why this is powerful or why this is profound? If I have n qubits, then it means I need, in order to describe a state, I need to 2 to the power n compressed number. What's such a big deal? If I have 300 electrons, even kindergartner can count to 300. But then I actually need 2 to the power 300 compressed number to describe a general state of 300 electron spins, right? And if you think about the number of atoms in the universe and also number of storage space available, you see that this is almost important. This is a huge number just for 300 atoms to describe that. We have not said that why superposition is important, but you see that superposition is profound. If it is profound, we probably can use it to do something special. One of the very hand-waving idea is that we can do quantum parallelism. Of course, this is not rigorous. If it is a superposition, for example, now I have 2 qubits, so I have 4 basis states, 2 to the power 2, right? So it can be in a linear combination of the 4 basis states for a state. And because quantum mechanics is linear, I apply an operation to it, then I will be able to compute each of them at the same time. Of course, this is just a hand-waving notation. We don't compute on the basis states, but just telling us that looks like we have a parallel universe. We do the computation all at the same time. Now, this is not a joke because I believe the physicists and philosophers, they have been debating what is the meaning of this thing. This is real, a very philosophical question. But for engineer, we don't care. As long as we can use it and earn money, that is fine, right? So that is the power of superposition. Now, then, how about if you have a superposition, you have a lot of information. 300 qubit, I have 2 to the power 80 compressed number. Yeah, you got a lot of good things, but how do you get the information? That is the weakness of quantum mechanics. In order to get the information, we need to perform a measurement. And what is a measurement? It's just like the spinning coin on the table. How do you see whether it's head or tail? I just stop it. Then it will either collapse to head or collapse to tail. And that is exactly the same for a state, a superposition state. If I do a measurement, it will collapse to either 0 or collapse to either 1. It will always collapse to the basis state randomly, except that the probability it will collapse to 0 and 1 will be proportional to the square of the magnitude of the corresponding coefficient. So since it's so random, I cannot get out. Since due to this reason, I cannot get alpha and beta directly and easily. This is a caveat about quantum computing. Many algorithms promise to exponentially speed up the computation, but you find that the data preparation and extraction actually can be slower than the classical computer. So that you need to be careful when someone came to you to ask for investment funding about this caveat, right? So that is one important property of quantum computer. Another is that we said besides superposition and measurement, one important thing is the entangled state. It used entanglement to perform some very special and speed up the operation. Of course, we will not go into detail because today is about the hardware. But one important thing, just remember, if I have 2 states and they are unentangled, here I have 0, 0, 0, 1, 1, 0, and 1, 1. And based on this, probably you remember this is a 2 qubit because I have 0, 1, 2, 3, right? I have 4 possible basis states. And here form a superposition state, right? This is a given superposition, a particular one. I can factorize it. Right? Let's ignore this tensor product. It's not that important. But the point is that it tells us that for some states, I can describe the whole system by just describing the individual system individually. So they are not tangled, they are not coupled. But there are some states such as this one. It is also a superposition state, except that the coefficient for 0, 1, and 1, 0 are 0. Means they don't have component. You can never separate them. So this is the entangled state. Okay, so we talk about superposition, entanglement, and that is the basics, right? And why we need to review that? Because when we go to the hardware, we will need to have hardware to implement all these things, right? So what is a quantum gate? This is also as an electrical engineer, we used to, before we learn quantum computing, we always have this misconception and thought that it must be like the IC design chip. We have a lot of transistor, a lot of gate length, gate NOR gate. And if you need 1 billion gate, you really need a large area, right? But quantum gates in a quantum computer is nothing but just the laser pulse or microwave pulse. So what it does is that you have a passive quantum object. You shoot a microwave or laser pulse to it and change its state accordingly, right? We will go into the detail later how we implement this in spin qubit and superconducting qubit. But the message is that no matter what we are doing, a quantum gate is just rotating the vector or the wave function or the state. Okay, so I like to use this as an analogy. Like myself is the qubit. I'm the physical object. And my state is the state of my mind. So when someone tries to manipulate me, or rotate me, they don't really rotate my physical body, but they keep telling me something. For example, my state was that I don't like to eat orange. And then my mom keeps saying orange is good, whatever. So this is the microwave pulse shooting to me. So it doesn't rotate me physically, but my mindset starts to realize that orange is good. And if eventually I rotate to the state that I love to eat orange. So this is exactly what happened in quantum computer. So because of this, when you heard people say that this algorithm need 1 billion or 1 trillion gates, then don't panic. Don't say, oh, Intel even cannot do that. How can you do 1 trillion gates? How can you lay out 1 trillion inverter, for example? No, you just say that you shoot 1 trillion microwave pulse to this qubit, right? So in terms of gates, we need some basic gates. Some are 1 qubit gates. We'll talk about that. Some of the 1 qubit gates and some are 2 qubit gates. For example, control NOT gates. Control NOT gates means that the states of another qubit depends on the states of 1 qubit, like B, depends on the states of another qubit. I will talk about that later. But these all have classical counterpart. You will find that it's all the logic that you already implemented in the classical computer. Of course, to be a quantum computer, you need to have some gate that can create superposition. This does not have classical counterparts. For example, the Hadamard gate. If you give it the basis state 0, like the head, if you give you a superposition of head and tail. Just imagine this gate is just like that. The coin is on the table, and the gate is that your hand spin it, then you become a superposition, right? So people like to use the broad sphere, which is a pretty elegant representation of the states of the qubit, right? So at each point on this broad sphere, represent a state. Just like my mindset, maybe the top is I love to eat orange. The bottom is I don't like orange. And then maybe here in between is I kind of like orange, but I also don't like orange. A superposition of this top and bottom, right? And all the gates is just rotating the states around this sphere. And because this is a rotation, you can now realize that if I can rotate in one direction, I must be able to rotate back. So all the quantum gates are reversible, which I will talk about a little bit later. Now, so this is for 1 qubit gates. I just rotate it, right? Then how about the 2 qubit gates? The important thing about quantum computer is that you need to have a set of so-called universal gates. This is just like in classical computation. If you have a NAND gate, you have a NOT gate and an AND gate, you can build any logic out of NOT gate and AND gate. Same here. it is proof that although sometimes it's just approximation, if you have a set of 1 qubit gate, then plus something called entanglement gate, then you will be able to build any algorithm, or at least to approximate any algorithm. So here, that's why we must talk about entanglement gate. And we will talk about this in this tutorial, right? And if someone comes to you say, I found a new architecture, but it doesn't come with an entanglement gate, then you know that it won't work, even it has very good 1 qubit gate. So what is entanglement? Entanglement gate. So one example, this is an example called C-NOT gate, control NOT, or sometimes called exclusive OR gate. So how does it work? If you just look at how it operates on different bases, right? We have 2 qubit now. So you can have a basis 0, 0, 0, 1, 1, 0, and 1, 1. We can just ignore this because of time, but we can see how it does it. If the first qubit, the left one, is 0, it does nothing. So because this is 0, so 0, 0 is still 0, 0. 0, 1, still 0, 1. So this is the input, this is the output. So it's just like identity gate at this moment. But if the first bit, which we call it the control qubit, is 1, it's going to apply a negation to the second qubit. So when it's 1, 0, because this is 1, it's going to make 0 to be 1. So 1, 0 becomes 1, 1. And 1, 1 becomes 1, 0. Okay, so this is the so-called control NOT gate. And you will see that in spin qubit and superconducting qubit, we don't implement the control NOT gate directly because the physics does not allow us to have this one to implement this easily. We will see that, but we can find the equivalent. So all we will do is just find all the 1 qubit gates plus the native entanglement gates of that technology and make them act as a control NOT gate. Right? Of course, you don't really need to have control NOT as long as your algorithm can do the entanglement, that is okay. But if we can prove that the entanglement gate is equivalent to this C-NOT gate, then we are sure that it can implement any algorithm. Okay, so that is the control NOT. A few characteristics of the quantum gate is that it's reversible, as I said earlier. If I give you the output of and LAN gate, and this is classical. I say the output is 1. None of you can tell me what the inputs are because it can be 0, 0, 1, and 1, 0. If I cannot tell you the input, it means I cannot reverse the state, right? And this consumes energy. Now, this is a control NOT gate. You will see that if you give me a pair of output, you say the output is 1, 1, and you told me that the gate is control NOT. I know that the input must be 1, 0. They are reversible and they consume no energy, right? So reversible also means that I can restore the state. And this is very intuitive because quantum computing is just based on quantum mechanics, which based on the Schrödinger equation. And Schrödinger equation, if there's no dissipative term, of course, you can always go back in time, right? You can derive what the previous state was. So that's why eventually I always emphasize, what is a quantum circuit? You start with a state, you apply different quantum gates, but quantum gate is what? Just laser pulse or microwave pulse. So I'm running from left to right, I do the computation. It is the flow of time, not the space. I'm not showing an IC chip that I have the input, inverter, LAN gates, and then adder, and then register. I'm not doing this. This is just at time 1, I apply U1, time 2, I apply U2, and eventually I get what I want, and then I measure it. Before I do the measurement, it is reversible. I can apply the inverse of the gate I've just applied. Okay, so this is a concept. Another important thing about quantum computing is about error correction. It's very difficult to do error correction. In classical computer, right, usually what we do is just do repetition code. If you try to transmit 0, you have noise. I just put many 0, and then you use majority vote. Maybe the middle one will get flipped, but because most of them are 0, then I know that it must be 0. But in quantum mechanics and quantum computing, there's something called no cloning theorem. You cannot copy a state that you do not know, okay? And it's also easy to understand. Classically, how do we copy a state? We read it and then copy. Even you say you don't read it, but your computer read it and then copy from the memory to another memory. Now, how can I read it? I need to do measurement. And what happens when we do measurement? It collapses, right? So it's just that I cannot copy the spin of a coin to the spin of another coin on how fast it spins or the angle. Because whenever I want to see what it is, it will collapse and I lose the information. And because of this, the idea is do something like syndrome measurement. There are many different types of algorithm, right? Which I don't know well either. But the main point is that maybe psi, this state is what you're interested in. It is the information you want to preserve. You try to entangle it with other qubit, which we call it the auxiliary qubit or ancillary qubit, that you don't care. But they are very important because if there's some error happen to the qubit I want, because they're entangled, it will be reflected in those auxiliary qubit. So I just measure the auxiliary qubit. I know what happened to my qubit already. So I'm not going to measure my qubit. I already know what happened to it. I just apply a gate to correct the error. This is the simplest form, right? So we are done with the basics, not related to hardware. So the last 8 minutes, I will talk about the basics of the hardware, and then based on which we will talk about the detail of the hardware. How can we build a quantum computer? DiVincenzo's criteria, he listed 5. 1, you need to have a scalable physical system. I think it's scalable and also well-characterized qubit. I think this is very common sense for everyone, right? Because we're talking about 2 qubits, you have 0 and 1 states. You better come up with a physical system that have 2 distinguishable states. If you cannot distinguish 0 and 1 from that system, it cannot be a good qubit. That is the first thing. Also, you cannot have many levels because I want to stay in the ground and the first excited state. If during the computation, let's say the atomic states jump to the 3rd level, then I lost all the information. It's not confined in the so-called Hilbert space I'm working on. So you need to have a well-separated and also well-defined 2 levels of space. Second is that you should be able to initialize it. This looks very trivial. Initialize the state to 0. But it is very important because many quantum algorithms rely on the initialization of the qubit, either at the beginning or at the middle of the algorithm. So you should be able to initialize it with high fidelity. Right? This is, again, not trivial. And also fast, because we might need to initialize it 1 million times throughout a big algorithm. And if you take 1 second to initialize, then you take 1 million seconds just for the initialization part. Then your quantum algorithm is not giving any advantage, right? You need to have a long coherence time or decoherence time. Before that, just because of the noise, we want to keep the state. And before the state loses information, we want to apply as much computation as possible, right? And then you need to have a universal set of quantum gates, which I just mentioned, 1 qubit gate plus an entanglement gate. So you can implement all the algorithm needed. And the last thing is also not trivial. You should be able to measure it and also selectively measure it. It's very important. You cannot say when I measure, all the qubit collapse. Because there are, again, many algorithms, you need to selectively measure a certain qubit. And based on the result, you decide what to do in the next step. For example, in quantum teleportation, okay? A dilemma is that if you have a long decoherence times, means, wow, you're well isolated from the world, right? Good. Maybe your decoherence time is 1 year. But it also means that it's difficult to manipulate the qubit. Because you have long decoherence time means you don't interact with the rest of the world. Of course, then the world, if you want to control it intentionally, it also takes a lot of time because the interaction is very weak, right? So I would say the quantum computer is like this at this moment, a well-organized physics lab. So maybe in 1970s, people doing all this atomic physics, they already have the quantum computer. But it's like maybe a whole room and only one qubit in that principle, right? But now you put them all together. So a quantum computer nowadays, again, is that you have some passive boring wave function sitting there. An electron spin, or maybe atoms, 5 atoms sitting there. Very boring. If you don't interact with them, they're just boring wave function. They evolve with time. But then you will shoot some microwave pulse to initialize it. You may shoot some microwave pulse to manipulate it, which is just a quantum gate. You also want to selectively read it out, right? And they should have different levels, but only 2 of them should appear during the computation. We don't want you to excite to the higher level. And we also need to be careful that there will be noise interacting with the environment, right? So the whole quantum computing process is just shoot the right frequency, right shape, right amplitude, right phase at the right time with the right duration. That is a quantum gate. And because there are so many rights, then you see that there are lots of engineering with high-speed electronics. Universal of quantum gates, there are 2 examples. One is that exclusive for gates and then arbitrary rotation about the XY axis of the Broad sphere, any angle. This is complete. Or you can also have this 3 discrete gates. This is not really complete, but if you apply many of them, they can approximate any quantum algorithm. So in this tutorial, our goal is to say that we will, let me admit the attendee, sorry. It is to say that we will show that the 2 architecture can implement the arbitrary 1 qubit gate and also 1 entanglement gate. Okay, and the final slide is that because you need 2 well-separated levels, then you should, what do you mean by well-separated? Everything is separated. The so-called well-separated related to the noise, and the major noise is the thermal noise. If you operate your quantum computer at room temperature, like here, the thermal noise is in the order of 25 millieV. For some quantum computer, for example, the superconducting quantum computer, the energy separation is only in the 0.02 MeV. So if the noise is so big, how can you distinguish 2 levels? And that's why we need to go to a much lower temperature with the noise energy about 10 times or more or less than the qubit separation, right? Otherwise, that's why we need direction refrigerator. We need laser cooling, for example, right? Otherwise, it will cause decoherence. It will lose the information. And there are 2 types of decoherence. One is, not 2 types, there are many decoherence, but 2 characteristic types, right? We use some characteristic decoherence time to measure how good a quantum computer is. One is that we put them at the excited state, 1. They're supposed to stay forever, but unfortunately they will decay, right? For example, here, this takes 290 microseconds characteristic time to lose most of the information. Another is the phase related to the phase decoherence. As we said earlier, superposition is very important. And when we have superposition, you do computation through interference also. If you lose the phase information, when it was 0 plus 1, now it becomes 0 minus 1, your algorithm will fail also, right? So these are 2 major characteristic types that we care about. Okay, so I think I will pass it to Imran to continue.